want to consider is you're gonna solve differential equations using Laplace transforms, right? Now, in order to do that, we need a couple more formula, right? Which would be these formula here, right? So what we want is Laplace transform for a derivative of a function, right? Alright, so in Laplace transform, we usually take Laplace transform of y of t, right? Now this y of t, obviously, it's a function of time t over here, right? Okay, so these formula that I'm talking about, instead of taking Laplace of y of t, right? What we're going to be looking at is Laplace of y prime of t, right? So instead of y of t over here, you have the derivative of the small y of t, but with respect to the time variable t, right? So y prime of t, right? And the formula that we would use is that Laplace of y prime of t is equal to s Laplace of y of t minus y0, right? Okay, so what's you want to notice on this left hand side, what you have is you have derivative of the function, you have y prime of t, right? But on this side over here on the right hand side, right, everything is in terms of y of t, right? So left hand side what you have is derivatives, and on the right hand side what you have is the original function, right? So in a sense you could look at this as integration, right? Because what you have is derivative on this side. So Laplace of derivatives is in terms of Laplace of the original function, and you get the y of t really by integrating y prime, right? You're not really going to actually be doing integration over here, right? And just making a point that on this side you have y prime, and on this side that you have y, right? So in a sense, what you're doing is you're expressing Laplace of y prime in terms of Laplace of y, right? So in a sense, what you're doing is you're actually integrating the y prime to get y, right? That if you want to look at it that way, but really what we're going to be doing is you're just going to be using this sort of formula when we solving differential equations, ordinary differential equations using Laplace transform, right? Now, where this formula comes from is you can use your definition of Laplace transform. So Laplace of y prime of t is, by definition, what you're going to do is you're going to multiply the y prime by e to the minus st, and you integrate from 0 to infinity, right? So I'm just using a definition of Laplace of y of t. This is indefinite integral, so I replace the infinity by r and take the limit as r goes to infinity. And over here, this is just integration, right? And now what you do is you use integration by parts on this, right? You use integration by parts. What you want to do is you want to eventually get an expression involving y of t, right? Involving y of t, right? So remember, when you're doing your integration by parts, you're going to choose a v and you're going to choose a du. The v you're going to differentiate, and the du you're going to integrate, right? When you're doing integration by parts. Okay, so you choose the du to be y prime dt, right? Which is this over here. So that when you integrate this y prime, what you get symbolically is y of t, right? Well, you get y of t. Right, so that's the idea really how this works. You use an integration by parts, and then you choose the du to be equal to y prime t dt, right? And then when you do your integration, you get the y of t, right? And then you go through your formula here, right? And going through your formula and checking certain things would in fact give me this formula for Laplace of y prime of t. Okay, so Laplace of y prime of t is s Laplace y of t minus y0, right? You can take a look at this proof if you want, right? But really, what I expect you to know is this formula for Laplace of y prime, right? Okay, and once you have this formula for Laplace of y prime of t, right, you could in fact use this to get you Laplace of second derivative of t, right? Okay, and the idea here is that to get Laplace of second derivative of t, right? You want to remember that second derivative is first derivative, and you differentiate it again, right? Okay, so Laplace of y double prime is Laplace of y prime differentiated, And now what you do is you use one application of your derivative formula for y prime that you have from above, right? So what you have is this function inside here, you're differentiating it, right? So Laplace of the derivative of y prime is s Laplace of y prime minus y prime 0, right? And then what you do is you use this formula again, right, for Laplace of y prime. And the Laplace of the y prime over here you can replace by s Laplace y of t minus y0, right? Okay, so what that gives you is that gives you, when you work this out, you get Laplace of your second derivative is s squared Laplace y of t minus sy0 minus y prime 0. Okay, all right. Okay, so these are the two main formula that we're going to be using when we're solving differential equations using Laplace transform, right? Okay, and if you want Laplace of, say, third derivative or fourth derivative, and so you can use this general formula here, right? So this general formula will work for when you for first derivative, second derivative, third derivative, fourth derivative, any order of derivative here, right? But then what the examples that we're going to look at in this class, the derivatives that we would look at would be second derivative and first derivative, right? And these are the formula that we're going to use, right? Okay. Let's see an example of using Laplace transform to solve a differential equation, right? Okay, so I want to solve this ordinary differential equation given initial conditions, right? Okay, so when we're doing our Laplace transform problems for solving differential equations, you typically you'd need these initial conditions, right? If you don't have the initial conditions, well, then your answer is going to end up having constants, right? But typically, initial conditions are going to be given to you, right? Okay, so we want to solve this differential equation using a Laplace transform, right? So what you do is, for this differential equation, you take Laplace transform on the left-hand side, on the right-hand side, right? So that's what we do over here, right? And on your left-hand side, right, what you do is you use your linearity of the Laplace transform, right? Which means that I can break up this sum over here into Laplace of second derivative, and then I can also pull constants out. So this sum of three functions here, I just take Laplace of them individually. W prime minus 3 Laplace of y prime plus 2 Laplace of y. And I also need to take Laplace of the right hand side, right? Now in this case, this is easy, right? This is just going to come from a table, right? And Laplace of an exponential e to the 3t is 1 on s minus 3. Okay, so far I have this here, right? And now what I do is I use my formula for Laplace of derivatives, right? Okay, so you know this over here, what I have is Laplace of second derivative and I have Laplace of first derivative, right? Okay, so I'm going to use my formula for Laplace of first derivative here, right? And Laplace of first derivative is s Laplace of y minus y0. Okay, so this Laplace of your first derivative, I replace it by a formula involving Laplace of y, right? And this Laplace of your second derivative, what I do is I use this formula over here, right? So your Laplace of your second derivative is also expressed in terms of Laplace of y and some initial conditions, right? Okay, so notice what happened over here, right? Once you use these two formula, right, one for Laplace of y prime and one for Laplace of y double prime, what happened is that now this entire expression is just involving the y, right? You no longer have any derivatives, and so, right, you no longer have any derivatives that would normally be part of a differential equation, right? Your y double prime and so got converted into a y here, and your y prime over here got converted to a y, right? Okay, right. So now this expression is just purely involving the function y of t and some initial conditions, right? Okay, so at this point in time, what you want to do is you want to put in your initial conditions. So you put in your initial conditions, and these are given to you, right? The y0 is equal to 0. and the y prime 0 is equal to 0, right? So when you put in these particularly simple initial conditions, you get 0 over here, right? So the sy 0 is just going to go to 0. The y prime 0 is just going to go to 0. This y 0 is just going to go to 0, right? So all you'd be left with in this, for this example, you'd be left with the s squared Laplace of y minus 3s Laplace of y plus 2 Laplace of y, right? Right. Okay, now when you solve a differential equation, right, the idea is that what you're trying to do is you're trying to figure out if you have this over here, what you're trying to do is you're trying to figure out what the function y is, right? Okay, so eventually when we work this out, what we will do is we will get the function y here, right? So this is what we're heading towards, right? But so far, what we have is we have this expression here, right? And okay, so first thing I would do here is I just use a little bit of notation. I just write the Laplace of y as big Y of s, right? Okay, so everywhere over here I write Laplace of y as big Y of s, right? And the idea now is, right, so we get to this point, and what we do now is we solve for the y of s, right? Right, so solving for the y of s on your left hand side here, what you're going to do is you're going to factor the y of s out, right? Notice everywhere here, each of these three terms you have a y of s, so you can factor it out, and so you have y of s times s squared minus 3s plus 2, right? And to determine the y of s, you just divide by this s squared minus 3s plus 2, right? So it'll go into the denominator here. So I end up with y of s is 1 on s squared minus 3s plus 2 times s minus 3 on the bottom, right? Okay, so this is the y of s, and to in fact get the y of t, right? So to get the solution that I want, right? So to get this solution, right, which is the y of t, right? To get the y of t, right? What I need to do is I need to take the Laplace inverse of this over here, right? Okay, so, and we know how to take Laplace inverse of, say, something like this, right? To take Laplace inverse of, say, something like this, right? This is not going to come directly from a table, so what you're going to do is you're going to use partial fractions here, right? And in order to use partial fractions, what you're going to do is first you try to factorize your denominator as much as possible, right? So here, this quadratic, we can actually factor as s minus 1 times s minus 2, right? So overall the denominator here is s minus 1 times s minus 2 times s minus 3, right? Okay, so the one on s minus 1, s minus 2, s minus 3, a partial fraction expansion for it. What you have is you have three linear factors, so you're just going to have a constant a for the first linear factor, constant b for your second linear factor, and constant c for the third linear factor, right? Okay, and now what you do is you clear your denominators, so you multiply both sides of this equality over here by s minus 1, s minus 2, s minus 3. Okay, and that would cause you to have just a 1 on the left hand side. And then once you multiply this, the s minus 1, s minus 2, s minus 3 on the right hand side, a times s minus 1 will cancel with this s minus 1, so you're going to get a s minus 2, s minus 3, right? And similarly, you'll get b s minus 1, s minus 3, and c s minus 1, s minus 2, right? And once you get to this point, what you're going to do is you need to figure out what the constants a, b, and c are, right? Okay, so we get to this point here, right? And now what we need to do is figure out what constants a, b, and c are, right? And easiest way to do that in this case is really just to substitute values, right? Okay, so if you substitute s is equal to 1, first of all, what you'd get is you'd get, well, substituting s is equal to 1 over here, right, gives you minus 1, right, minus 2, which is this minus 1, minus 2. Substituting s is equal to 1 gives me a 0 here, and then a minus 2 here, right? And substituting s is equal to 1 gives me a 0 here and a minus 1 over here, right? And why I'm substituting s is equal to 1 is because I have 0 times this b over here, so this will just drop off for me. And I get 0 times the c, so this would also just drop off. So what I end up with is 2a, 1 is equal to 2a, which gives me a is equal to half, right? Similarly, when I substitute s is equal to 2, right, the term with the a is going to drop off. The term with the c is going to drop off. And what I will have is I'll have a 2 minus 1, which is a 1 over here, and a 2 minus 3, which is a minus 1. So I'd have a 1 and minus 1. This is 0 here, and this is 0 here, so I have minus b is equal to 1, which gives me b is equal to minus 1, right? And then finally, substituting s is equal to 3 would give me 0 for the a, 0. Well, the term in the a will drop off to 0. The term in the b will drop off for 0, right? And all I'm left with is this term for the c here, right? When I substitute s is equal to 3, I have 2 here and 1 here. So I have 2c. Okay, so in this equality here, I'll have 0 here, 0 here. And then 2c is equal to 1, which gives me c is equal to half, right? Right, so that allows me to figure out what my constants are, right? The a is equal to half, the b is equal to minus 1, and the c is equal to half, right? Okay, so the y of s is, I wrote the y of s in terms of partial fractions. This is the y of s inside here. And to get what I want, right, the y of t, I need to take Laplace inverse of the y of s, right? And Laplace inverse of the y of s is, this is the y of s over here. You factorize your denominator, then you use partial fractions, right? And now that you have this broken up into these fractions over here, right, these simple fractions, you use your linearity to split this up, right? You use your linearity, so you get a half times 1 on s minus 1. Okay, so half times Laplace inverse of 1 on s minus 1, minus 1 times Laplace inverse of 1 on s minus 2, and then plus a half Laplace inverse of 1 on s minus 3. And at this point in time, what you do is you use your formula for Laplace inverse, right? And this really is just going to come straight from a table. Laplace on 1 on s minus 1, right? You see I have 1 on s minus a over here, and Laplace inverse of the 1 on s minus a is a e to the at, right? So Laplace inverse of this 1 on s minus 1 is going to be an exponential. So what I'd have from this is Laplace inverse of the 1 on s minus 1 is e to the t, right? And then Laplace inverse of the 1 on s minus 2 would be e to the 2t, right? With a minus sign out in front there, right? And then over here, I'm going to get Laplace inverse of 1 on s minus 3 is e to the 3t times the half, right? Okay, so the required answer, y of t, is this function of t over here, right? And that is what's stated here, right? So the solution of my differential equation with given initial conditions, also called an initial value problem, the solution of this differential equation is this y of t. So let's see a second example of solving ordinary differential equation using Laplace transform, right? Okay, so this one here, this is from a past paper. It's saying that you have a mass spring system with an external forcing f of t is modeled by this following initial value problem, right? Okay, so really they're just telling you that your situation here is modeled by this differential equation, and what you need to do is you need to solve the differential equation, right? You don't in fact really need to do any modeling and so, right, to realize that this is a damped harmonic motion or anything like that, right? Really, they're just giving you the differential equation, and in this case you just need to solve it, right? Okay, so we have this second order differential equation and you want to solve, right? Now your function here, okay, as compared to the previous example that we looked at, right, this function over here is not get Laplace of this, right? This is not going to come directly from a table because this is a piecewise defined function, right? Okay, and to get Laplace of a piecewise defined function, how we're going to do it is we're going to use the definition of Laplace transform, right? So that is one way in which this differential equation problem here is different from the one that I just looked at, right? The one that I just looked at, basically the right hand side is pretty easy, right? This e to the 3t, to get the Laplace of it, it was just going to come directly from a table. Laplace of e to the 3t is 1 on s minus 3, right? In this case, this right hand side, your function isn't that straightforward, right? And how we're going to get Laplace of this piecewise defined function is to use the definition of Laplace transform, right? Anyway, okay, so let's solve this using a Laplace transform, right? And the method is basically the same as what we did for the previous example, right? You take Laplace transform on both sides of your differential equation, right? So I take Laplace transform on both sides of my differential equation. I use linearity to break up my left-hand side, right? And I still need to work out Laplace of f of t, right? And now what I do is I use my formula for Laplace of second derivative and Laplace of first derivative. And you want to remember what those are, right? Laplace of first and second derivatives, those formula, these over here, right? So Laplace of first derivative is S Laplace of, if I have y prime, then it's S Laplace y of t minus y0, right? In this case, I have Laplace of x prime, but it's the same idea, right? So what I'd have is S Laplace of x, right, minus x0. And what I'm doing is I'm multiplying everything by 5, right? And similarly, Laplace of y double prime, this is, okay, I have Laplace of x double prime over here, so what I'd use is the formula for Laplace of second derivative. So what I get is s squared Laplace of x minus s x0 minus x prime 0, right? Okay, and now what I do is I put in my initial conditions, right? So when I put in the initial conditions that were given to me, which are these initial conditions over here, these initial conditions are both 0, right? So I'll get a 0 here and I'll get a 0 here, right? Okay, and I also get a 0 over here. The 5 times x0 is going to be 0, right? So it will simplify down to this here, right? S squared Laplace of x plus 5s Laplace of x plus 4 Laplace of x is equal to Laplace of f of t, right? Now I still need to work out what Laplace of f of t is, right? But Laplace of f of t is piecewise defined, right? And what you do is you use a definition of, in the case of when you have something that's piecewise defined, what we're going to do is you're going to use a definition of the Laplace transform, right, which is the integral from 0 to infinity of e to the minus st f of t, right, times f of t, right? But here I'm integrating from 0 to infinity, right? But this integral I can split according to the intervals over here, right? So here I have two intervals, 0 to 2, and then 2 to infinity, right? So this integral from 0 to infinity I split into integral from 0 to 2, and then from 2 to infinity, right? Okay, so now that I have that, right, now that I have it split according to my intervals, then I put in the information as to what the f of t is, right? So between 0 and 2, the f of t is equal to 1, so I put that in. And between 2 and infinity, the f of t is equal to 0, so I put that in over there, right? Okay, so over here, what I'm doing is I'm integrating 0, so this will just drop off for me. And over here, what I'm doing is I'm integrating e to the minus st, right? Okay, so this one over here with a 0 in it, this would be integrating 0, so this will just drop off, right? And all I'm left with is the integral of the e to the minus st between 0 and 2, which is this here, right? So you integrate the e to the minus st, you're going to divide by a minus s over here, and then put in your values, your limits, t is equal to 0 and t is equal to 2. And what you will get is when you put in t is equal to 0, you'll get e to the 0, which is 1, divided by the s. And for the t is equal to 0, you'd subtract. So you get minus 1 on s, which is this plus 1 on s. And when you put in t is equal to 2, you're going to get minus 2s on s, right, with a minus sign out in front, which is this, right? So the Laplace of the f of t, the Laplace of this f of t, right, which we did by first principles, turns out to be this 1 on s minus e to the minus 2s on s, right? Okay, so now I know what this Laplace of f of t is, I can substitute it into equation 1, right? Alright, so I substitute this expression for Laplace of f of t into equation 1, right? And what I do now is I can factor the Laplace of x on the left-hand side, right? Okay, and so factor in the Laplace of x gives me s squared plus 5s plus 4, right? And then I have, this is my Laplace of f of t, right? Okay, now the goal over here is to solve Laplace of x, right? How I actually did this is I first factorized over here, right? Okay, you don't need to do it this way. You could actually, and it's probably better if you just divide by both sides of this equation by the s squared plus 5s plus 4, right? In order to solve for the Laplace of x, right? Okay, but here I factorized this, right? And this is correct, right? It works out, right? Okay, so the s squared plus 5s plus 4, I can factorize as s plus 1 times s plus 4, right? And now what I want to do is I want to solve for the Laplace of x, first of all, right? Because remember what I want to do, I want to eventually get the x of t, right? Okay, so the x is, right? So I want to get the x of t, and solving for the Laplace of x is an intermediate step over here, right? Okay, right. So now that I have Laplace of x is equal to this expression over here, what I need to do is I need to get x, right? And x is in fact the Laplace, x is the Laplace inverse of this expression over here, right? So I need to get Laplace inverse of this expression. And to get Laplace inverse of this expression, well, it's best if you just do this in pieces, right? So you get Laplace inverse of this fraction, first of all. And then you get Laplace inverse of this expression here with the exponential e to the minus 2s, right? Now, to get Laplace inverse of this 1 on s times s plus 1 times s plus 4, right? What you do is you'd use a partial fraction expansion, right? And we just saw how to do this. So you use your partial fraction expansion, and the form of your partial fraction expansion would be based on the factors in the denominator. Here I just have linear factors, so I'll get a constant over each of my linear factors here, right? Next thing you do is you clear your denominators, and once you clear your denominators, in this case when you have linear factors, it's easiest to just substitute values, right? Okay, so when you substitute your values, you will get a is equal to a quarter, b is equal to 1/3, c is equal to half, right? Okay, so that allows me to express this in terms of partial fractions. So I get that this 1 on s plus 1 times s plus 4 is a quarter times 1 on s minus 1/3 1 on s plus 1 plus a half 1 on s plus 4, right? Plus 1/12 1 on s plus 4. Okay, and also what I need to do is I need to get Laplace inverse of this expression here, right? Now, in order to do that, what I need to do is I need to use the t-shift that I talked about in the previous lecture, right? Okay, so I'm using this t-shift formula, right, to get Laplace inverse of the e to the minus 2s on s plus 1, or s plus 4, right? Okay, so what do I do over here, right? Well, if I want to get Laplace inverse of this, right, what you want to do is you want to figure out what the y of s is, right? And the y of s in this case is in fact 1 on s plus 1 on s times s plus 1 times s plus 4, right? What I did over here is this over here, right? So it's e to the minus 2s, right? I pull that out, and this over here, the y of s in this case 1 on s plus 1 s plus 4 is actually the same as this over here, right? And this over here had this partial fraction expansion, right? It had this partial fraction expansion. So what I do is this this e to the minus 2s times 1 on s plus 1 s plus 4, right? I wrote it in terms of partial fractions, right? And now what I need to do is I need to get Laplace inverse of this e to the minus 2s times this, right? Okay, so before I use the t-shift to work this out, let's just get we want to work out Laplace inverse of this entire thing, right? Now working out Laplace inverse by your linearity, you can get to get the Laplace inverse of this sum over here, right, what you're going to do is you're just going to take Laplace inverse of each of the terms in your sum, right? Okay, so here I have 1 on s, and when I take Laplace inverse of 1 on s, what I will get is when I take Laplace inverse of 1 on s, I will in fact get 1, right? So the Laplace inverse of 1 on s will be 1, so I'll get a quarter times 1, right? Laplace inverse of the 1 on s plus 1, I will use this formula here, right? And using this formula here would give me that the Laplace inverse of the 1 on s plus 1 is e to the minus t, right? So I have 1/3 e to the minus t, right? Okay, and then over here, right, Laplace inverse of this 1/12 times 1 on s plus 4. Again, what I do is I look at this 1 on s plus 4 and I take Laplace inverse of that. And again, what I'm doing is I'm using my formula for Laplace of an exponential. So over here, what I will get is e to the minus 4t, right? Okay, so each of these terms over here, I got Laplace inverse of it, right? Now, alright, so we just found Laplace inverse of the 1 on s times s plus 1 times s plus 4, right? And now what we want to do is we want to get the Laplace of the e to the minus 2s on the same denominator, s plus times s plus 1 times s plus 4, right? Okay, so how we're going to do this is we're going to use a T-shift formula, right? And remember what your T-shift formula looks like. It looks like this over here, right? Okay, and when you're using T-shift formula, basically two things you need to identify. You need to identify the T0 here, and you need to identify the y of s, right? And notice how this is written. This is written as e to the minus st0 times the y of s, right? So first we want to rewrite this over here in this sort of form, right? And I do that here, right? Okay, so the e to the minus 2s on s times s plus 1 times s plus 4, I can write this way as e to the minus 2s on 1 over s plus 1 times s plus 4, right? And you see the thing is over here, right, this 1 on s times s plus 1 times s plus 4, right? I already did the partial fraction expansion for that, right? The partial fraction expansion for the 1 on s plus 1, s plus 4 is of this form, and I figured out what the a, b, and c are already, right? So matter of fact, the partial fraction expansion for the 1 times s plus 1 times s plus 4, right, is these first three fractions over here, right? Okay, so this 1 on s plus 1 times s plus 4, right, I can write in terms of partial fractions here, right? And this here, this is the y of s, right? So in your T-shift formula, this is going to be the big Y of s, right? Okay, so the big Y of s would be these three fractions here, right? I have it written here. And when you're using T-shift formula, what you would need is, when you're using your T-shift formula, as I said, what you need is the big Y of s, and then from the big Y of s, you get the small y, right? So the small y is the Laplace inverse of the big Y of s, right? So this is the big Y of s, and I need the small y, and the small y is the inverse Laplace transform of this. And we actually did that already, right? The inverse Laplace transform of the big Y of s. This is going to be a quarter minus 1/3 e to the minus t plus a half e to the minus 4t, right? Okay, so this is the small y that's in this formula over here, right? And now what I want to get is I want to get Laplace inverse of the e to the minus 2s with these three fractions over here, right? Okay, so the t0 is equal to 2, right? The big Y of s would be these three partial fractions here, right? And the small y, we figured out that that's going to be the quarter minus 1/3 e to the minus t plus a half e to the minus 4t, right? Okay, now when you're using t-shift, right, and you have e to the minus st0ys, right, what you're going to have is heavy side ht minus t0. times the yt minus t0, right? So this is using your t-shift formula. The t0 in this case is 2, so I have ht minus 2 small yt minus 2, right? Okay, and how you get the small yt minus 2 is you get it from the small yt, right? And wherever you see the t here in this expression, you replace the t by t minus 2, right? So this is the y of t minus 2 in order to get it. Over here, this e to the minus t is now going to become e to the minus t minus 2. The e to the minus 4t is going to be now going to become e to the minus 4 times t minus 2, right? So this is the y t minus 2, right? So Laplace inverse of what I want, right? So Laplace inverse of this exponential on the s plus 1, s plus 4 is equal to this, which is equal to this over here, right? Which is equal to the ht minus 2, yt minus 2. And I figured out what the yt minus 2. So this Laplace inverse of this e to the minus 2s, s plus 1 and s plus 4, right, which is the same as this, is equal to this heavy side times the quarter minus 1/3 e to the minus t minus 2 plus a half e to the minus 4 times t minus 2. And that's exactly what I have over here, right? Okay, so to figure out what the given the Laplace of x is equal to this function of s, right? To get the actual solution. Okay, so what I want is a solution of my differential equation, right? I want the x of t, right? Okay, and to get the solution, the x of t, right? What I'm going to be doing is I'm taking Laplace inverse of this, right? And to take Laplace inverse of this, you use linearity to take Laplace inverse of the first fraction here. And the first fraction, this one itself, you're going to split into partial fractions. And for this second fraction over here, what you're going to do is you're going to use t-shift formula to work this out, right? And the working for the t-shift formula to work it out is over here.